Well, hello, everybody. Thank you so much for joining. As John said, this is John Aram with Woven Electronics. Strange times we're in right now, so we're going to make the best of it by trying to use technology. I will move through this at a pace such that we can get done in an appropriate amount of time, and hope to God my technology works for us. The first thing I want to talk about is just some confusion because as you saw on the first screen, it said Collins Aerospace, but we're talking about Woven Electronics. Woven Electronics has been through several acquisitions. We were part of BE Aerospace. BE Aerospace was acquired by Rockwell Collins. Rockwell Collins was then promptly acquired by United Technologies Aerospace Systems, and the name Collins Aerospace was born there in a fairly recent development. United Technologies acquired Raytheon. Collins Aerospace will remain a standalone business within the new Raytheon Technologies organization. And really, outside of our shirts and our business cards, not much has changed for Woven Electronics. We're part of a much larger organization that gives us a whole bunch of stability that we appreciate. But we have been around for 50-some years in the complex harness environment, working predominantly with the aerospace and defense industry. If we look at this screen, this shows our most common customers. Certainly always looking for additional customers, but these are the folks that we do business. We understand the aerospace and defense world and how it works, and that's really a strong suit for us. As we start to look through some of the platforms that Woven Electronics is part of, we see that we're on an enormous amount of things that fly. On several of these aircraft, we have components that are involved in the radar systems. Some of these aircraft we have other components, and some we actually have airframe wiring. So it really starts to beg the question as to why the overwhelming majority of what we do flies, and we'll talk about that shortly. We are based in Simpsonville, South Carolina. Our facility is 100% domestic. We don't do anything in Mexico, at least not for Woven Electronics. We have a great deal of land. We've got about 100,000 square feet here. 75% of it is manufacturing. We have a very large piece of land, so it's really ripe for expansion. Currently, we're running one shift. We have the ability, and sometimes we flex into multiple shifts. And as I said, everything is 100% domestic. We're running about 308 employees. That goes up and down. 26 engineers, and a bulk of the front office staff, of course, is off-site right now. Relative to our quality system, I just want to mention that we are AS9100B certified. That really mandates much of our structure, and it ensures that what we agree to build for a customer is what they will get. And sometimes this requires some back and forth to make sure that all drawings are in alignment. But the benefit of that is the absolute assurance that what comes out of the factory is in complete alignment with the documentation provided. As I said, when we look at what we are currently installed on, the overwhelming majority of it is in flight. And when we started to do some analysis, we went back and looked at programs that we participated in. And what we found was that the problems that we solved in the overwhelming majority of those instances were space and weight issues. Either we were able to get things into a space that a typical round wire wouldn't, or we were able to get some densities that other people couldn't do, or we designed some componentry that shaved weight out. So space and weight become very strong factors in what we provide the customer. And in addition to that, sort of in concert with the harnesses, oftentimes we have methods which will reduce installation costs and provide some mechanical solutions. But the bottom line is that our intent is to build you something that saves you space and weight and time to install, and we do that on time and to print. Here's a graphic that just shows you in some instances we were able to save as much as 80% in size, you know, a 50% installed cost savings, some lower maintenance costs, and some higher reliability. And some of that is by virtue of some technologies that we can offer you, which we're going to show you. So just going through into our capabilities, we have established a quick turn or a prototype line, if you will. It is owned by our engineering staff. We staff it with some of our tier 1 assemblers, so some of the best hands in our facility. But we're managing this through engineering. And what that does for us is it enables us to take some concepts that we might work with a customer and do some initial designs and builds, you know, sometimes with 3D printed parts and that sort of thing, so we can do test fits. But we'd like to be able to turn those things in 1 to 2 weeks after we receive the materials. The materials are the bane of our very existence. Connectors are often very long lead, especially in this environment where some of our connector vendors have been shut down due to COVID. But if we have the material, or if our customer has the material, we'd be able to turn a prototype in 1 to 2 weeks. If we look at the overall range of our product capabilities, we are fairly full spectrum, and that differs us from many of our competitors. We do RF cables and harnesses. We do fiber optics. We have the ability to weave cables, as we'll talk about, and we also have machine over-braiding capability in-house. We do both over-molded as well as metal back shell connectors. We have the ability to go beyond the cable and do full box builds or secondary packaging. And we also have the ability to mold full cables as well as just the shells. When we talk about woven cables, and I don't mean the brand name woven, I mean just cables that are woven together, there's a couple of reasons that people would do this. And I should stop here and say that we have the capability to weave cables. It is about 25% of our overall business. The bulk of what we do is in some way, shape, or form round wire, but we have this capability to gain some densities and do some things by virtue of our weaving capability that other folks wouldn't be able to do. But if we look at this graphic in the upper left, you've got a typical ribbonized cable, and what that does is it increases density. We could put multiple layers of cable in there. It is more effective in terms of bending in a certain direction. It doesn't put as much attention on contacts within connectors. So there's some real benefit in terms of doing that. We also have the ability to, in some areas, put increased amounts of fabric so that we can do some abrasion protection as well. But if you look at the right-hand picture that says cellular cable, in that instances, we're able to take bundles of cable, which might serve different purposes or have different electrical requirements, and bundle them and weave them separately within a larger overall weave. And this could be for some shielding effectiveness, or it could be because that gets routed elsewhere in the system. So there's a number of things that we can do in that respect. The photo on the bottom that says wire organization, that's actually a flat cable that goes round for a period of inches and then goes back to flat. But it might have to go through a constrained area or something of that nature. And we're also able to program breakouts. If we had an inbox build, we can weave the breakouts such that when the assembly is completed, it drops right into where it's supposed to go, thereby saving some time and installed cost. We manufacture a product that we call our CIC cable, or our controlled impedance cable. This product could deem a complete conversation all by itself, but the fundamental concept here is that we're able to weave a bunch of individual magnet wires into some configurations that can give us near coax-like performance, or it can be used as a replacement or as an alternative to flex circuits. And the photograph that you see at the top, those are the individual wires woven, and you can see that when you weave something, you have a natural sinusoidal pattern. And what we do is we're able to play with the power and signal lines such that they're either in phase with each other or out of phase with each other. We can put different grounding situations in place. Each design is specific to the customer's requirements, but normally speaking, the red and the blue are power and signal, and the green is ground. But the photograph below shows an instance where we replaced that stack of coax cable with that two-layer piece of our CIC cable and saved about an 80% space and weight benefit. The way that we manage, here's a few examples of either a balanced line configuration or a single line or a single-ended configuration. And again, that's just playing with the distance between the lines and the configuration of whether they're in phase or out of phase, whether there's grounding in between, or how we determine we're going to meet your needs. There are some constraints to this. We can only get to about 1.3 gigahertz. We do have some length constraints, but there are some significant benefits in terms of space and weight with this product. This is an example. What we do is we bring the CI cable to a circuit board, and then the connector is then mounted to the other side of the circuit board. Usually we'll house that into a custom designed back shell. Sometimes it can be overmolded if we see fit. There are a few instances where we can go directly into the connector, but we really prefer to drop to a small board. Here are some examples of some customized RF assemblies that we've done, some of which are woven, some of which are not, some of which show some custom back shell designs. But these are the sort of things that we're able to provide you. There are some additional, we call optimized RF assemblies. We can do full silicone encapsulation. The photograph in the upper left is actually from a weapon. It's about 6 feet long, and that whole system gets mounted, gets basically glued to the outside of a missile. Fortunately, it's just a one-time use situation. So to me, it always smelled of somebody forgot to put the cabling in the design, and we had to put it on the outside. We also have a mechanical assembly shown on the right side, and then some weaving shown down at the bottom, and we'll talk a little bit more about those. Here's some examples of some of our airframe braiding capabilities. We have the ability to use both metal and textile in our braiding applications. The photograph with on the upper right-hand corner shows a very, very complex multi-leg system, and that was Kevlar, and then stainless steel, and then another layer of Kevlar. So a very, very complex assembly that we were able to do, and that's no small task. Here's some examples of some packaging and box build assembly. The photograph that you see at the bottom left with the blue background is a large program worked on by Megahertz that uses a lot of our controlled impedance cable, and you can see how much space that all saved in that system by virtue of the CI cable. If that were round wire, that would be significantly larger, and it wouldn't have fit in the application. Here's a few examples of molded assemblies. This is not a large part of our business. We do have the ability to do that. We've got injection molding as well as just cavity pour type molding that we can do. There's some benefits in terms of protection. The difficulty is that once it's cast, that we can't uncast it, so the entire assembly would need to be replaced if there were some problems further down the road. We do a great deal of custom designed back shells. We design the shells and we have a partner company build them for us, so we don't have machining capability necessarily in-house. One of the things that you'll see fairly frequently from us are these multi-port back shells, as you see in the bottom left and right. The benefit there is on the left side, we've got 4 ports coming into the back shell. Conventional harness design oftentimes will tie those 4 legs further up the assembly, and we have to tie all the individual shields together and then bring it into the back shell in a single point. The shielding effectiveness by bringing all 4 individual legs into the back shell and then banding them to the shell is much higher. It also saves us a good deal of labor by bringing it in that way. So we tend to want to talk to you about multi-port back shell configurations, but also we can do odd angles or odd shapes or things that you're not going to find in a back shell catalog, and that's a benefit that we bring. And what that oftentimes does for us is it enables us to get something into a space that you wouldn't normally be able to do with off-the-shelf back shells. I want to talk about a couple of specific designs that we did, some problems that were brought to us, and how we solved them. This particular instance is on the Boeing 777 aircraft. The cargo door had a round wire assembly that we built, and with each opening of that door, the harness was pulling on pins in the circular connector and compressing on the other side of that round wire. And so we had pretty consistent failures that were occurring. So what we did was we broke out that round wire into a flat configuration. And our weaving process enables us to systematically give extra fabric. And what we did, if you look at the right-hand photograph, there's a little bit of fabric that goes left and right of the wire itself. And we use that area to clamp, those blue clamps, clamp the harness and hold it in place. And then that allows a hinge point for the harness very easily across the door hinge. And in doing that, we essentially eliminated any failures that the customer was seeing, and those are still in flight today. And even a new version of that has been designed on the next generation 777. This is an example. Almost all of the wiring in the engine rotation section of the V-22 aircraft is woven wire. We worked very closely with Bell and Boeing back in the early development of this aircraft. These harnesses are layers of Teflon jacketed wire with Teflon yarn stacked upon each other. And the reason for the Teflon is that it allows the cable to move onto itself fairly effortlessly. But one of the challenges that we faced when they were installing these was that they would plug a connector in on one side of the aircraft and then yank 20 feet of cable as hard as they could to fish it through. And then in doing so, they would pull contacts from the connectors. So we were able to design some bracketry that clamped the harness down in certain places and prevented any forces from being pulled on the connector when they did their inevitable yank through the aircraft. This is an example on F-35 where we had a 38999 connector and an ultra-high density connector. In between the two were a very large bundle of twin-ax cable, so much so that it could not fit into the space that was allotted for it. And what we did was we came in with multiple layers of our controlled impedance cable, which is able to withstand the jet fuel and the PAO environment that existed inside that aircraft. And we serpentined that CI cable, or those bundles of CI cable, into an S shape, as you see in the top photograph. And we put right angle. They're actually back shells now. The photograph shows the initial molding, but they're actually back shells now. And what we're able to do is essentially make those connectors back to back when they're installed in the configuration. So that enabled us to get it into where it had to go, and it still was able to give them the performance, 128 signals in this particular case. We did not have to put additional shielding on this environment because of the controlled impedance design. So it was much less expensive, and it performed much better than the other alternative, which was a flex circuit. This is an example of an overhead circuit breaker panel that was installed in an aircraft using conventional wiring. We redesigned that into a woven configuration. It enabled things to be very easily traced if there was a problem with any of the relays. More importantly, it enabled the door to stay shut, which was a problem for this particular aircraft, and they got much better solution going in this direction. And this is probably our largest cable assembly. It is the vertical launch system from Lockheed Martin. That box that you see is approximately 6 feet long, approximately 2 feet square. There are 7,000 terminations in that assembly, 28 sub-assemblies. The story of this is that its initial configuration, they used to have to shove the wires in the box with a 2x4 and then close the doors. I don't have that verified, but that's the folklore in our factory. But then they came to us and asked us to add 400 additional wires for a system upgrade. And there was just no room for that. So what we did was we took bundles of cable, depending on where they routed, and removed the shielding and jacketing from the individual wires and bound them together, and then wove a conductive yarn around the larger bundle, created the ground shield there, significantly reduced the overall bundle size, and we're able to get those 400 wires in, and in fact reduce the overall size by about 30%, and made it 20% lighter, which is sort of inconsequential on a ship, but we also made it less expensive by utilizing some of these weaving capabilities. So that is a very, very fast run through of our capabilities, just to be sensitive to your time. And John, I think we're going to open the questions.